everyone. I'm a first-year PhD student in the Trustworthy System team in UNSW. So I'll talk about verifying device drivers with Pancake and its tool chains. So that will include the device driver verification that we've been working on in the past year, and as well as some future possible plans. So I'm going to try to generalize the idea into Linux OS subsystem verification, but we'll also talk about the established approach and performance of the device driver study case. So the problem that we're looking at is that we want some approach to verify the Linux OS subsystems, but we don't have one approach yet. So just looking at Linux OS in terms of verification, there are a few points that we would like to achieve. So the first one is that we want to have binary level verification to have a complete story. Second one is that we wanted fairly low effort. As Gunnar mentioned, that we want to repeat that verification approach in possibly multiple systems, so it can't be like an one-off effort. And the best would be that the approach has some way of dealing concurrent modular components, which is like the design principle of Linux OS. So now, of course, by my talk title, I'm going to talk about one possible approach using Pancake. So just to have a bit of recap of the Pancake programming language from Gunnar's talk, basically the main features that we care about in terms of verification is that first one is its target is system level programs, so very suitable for Linux OS systems like device drivers, network services, block services, and so on. And it has a verified compiler, meaning that the source code properties are also established at the binary level. So that makes it easier for binary verification because we don't have to go into the compiled level binary code, and that saves potentially a lot of verification effort. But another main tool that I want to talk about is the Pancake to Viper transpilation front-end that enables further automation. So just some brief recap about Viper. Viper is an automated theorem prover infrastructure developed by people in ETH Zurich. It has its own intermediate language for modeling so that user can have their system model in the Viper language, and that connects to SMT solver backends for verification. So it has various front end for programming language, including Python, Go, Rust already. The way it works is that the transpiler, for example, Nagini for Python, Gobra for Go, and Pristi for Rust, it translates the source program language into the Viper intermediate language and fits into SMT solver so that we can have properties of the source program. And now we have the Pancake frontend. So that was originally written by a visiting student from ETH, Alessandra, last year. So I think the best way to do this is a little demo of how this front end works. Great. I'll probably need to zoom in a bit. So just to start, that we have normal declaration. So that's actually the new global variable functionality that just got introduced about 1 month ago. We have, Pancake has standard arithmetic operation and bit operation like bit shift and so on. And we can check out, so just standard thing that it prints 3. And then there's C-like control flow. So we have this if, and then we have else. Well, I don't have else code here, but we have while loop that probably just works as expected. And then there's a bit more lower level operation of memory load and store, so a bit like assembly style. So here, this is the base pointer of that just points to the beginning of Pancake internal memory, and that just stands for storing 42, the value 42 into the base pointer in that memory location, and then we load it into our local stack variable x. And if I print this out, it should just print 42, which is what we stored at the base pointer. So that's just a brief overview of Pancake. Probably, hopefully it's similar to C language. Undergrad student has been using it pretty well, so we hope that's sort of friendly to system programmers. In terms of the transpilation into Viper, so we have the annotation that's in the Viper intermediate language style. So this one gives us access to write to the variable A1. We have precondition that it equals to 1, and by our operation, the postcondition that of A1 should be 3. So we transpile. And then we have the pre-post condition of our Viper model. That's just the same as what we have in Pancake. So that gives us a Viper model of our Pancake program. So we can also connect our Viper model output to say our device model by having some uninterpreted, non-deterministic function. Like here we load 42 from this 42 int, 46 int, 64 int from some shared memory address, and the post condition is bounded 64, meaning that the return can be any integer within that range. So if we want to have some device model, we can just say like if our address is equal to some, say like device register, then our return value would be within a more constrained range of non-deterministic value, and that can connect to our Viper model of our Pancake program. So that's just a brief overview. So the demo, you can play around with it yourself in the trustworthy.systems Pancake playground. Hopefully that link works. Right, so basically the workflow of our device driver verification is that we implement a program in Pancake, we add the annotation of the specs in our code, and the transpiler will generate a Viper model of our program. We then add our environment assumptions about the hardware device and the neighboring component in the style that we just seen in Viper as a Viper model. And together we'll feed that into the Viper verification, the prover, to tell if our code meets the spec. So Although currently the transpiler is part of the trusted computing base, there is plan to verify the transpiler formally. So Pancake has formal semantics, and there is work just last year that has a subset of formal semantics of the Viper language. So it's possible to have this workflow entirely verified. So the transpiler and the Viper infrastructure are kind of like off-the-shelf tool that we can already use. So apart from the manual annotation and our model, the rest of the workflow is basically automated. And with Pancake's verified compiler, so that means we can sort of have a fairly low effort of having a verification stack from spec to binary. So now I'm going to show a bit of the results from the case study of the Ethernet driver verification. So we took an Ethernet driver that was originally written in C and rewrote it in Pancake. So here's the line number count of the Pancake driver and annotation and neighboring component models. So the yellow highlight is the Pancake code, and the orange highlight is the Viper code. So from my experience, I think the Pancake driver implementation part is fairly easy. The annotations and models took a bit longer, so the entire verification took about 3 to 4 months, but that also includes my pitfall of my firstly trying verification and also involved in testing and helping the development of the transpiler. So the final verification runs about 1 to 2 hours on standard laptop. So I think that's kind of okay for verification. Right, so the properties that we verified are mostly, first one is device safety, meaning that when the driver interacts with the device registers, driver doesn't violate the device protocol. And the second one is data integrity. That's mostly done by inline assertions. So saying that like in the SDDF context that when driver transfer data from device to its destination, the data remains unchanged. And also memory isolation is a way of using Viper's permission access, that the function within driver only has access to memory that it needs to access and doesn't have access to other regions. So for example, the receive path of the driver only has access to receive and doesn't have access to transmit part of the memory region. And here's the performance data of the verified Pancake driver versus the unverified C driver in terms of receive throughput and the driver CPU utilization. So for throughput, the driver basically behaves the same, but we can see that there is some overhead in the driver CPU utilization, so it's about 20%, and there are active optimization work going on in to reduce the overhead. So just to recap what's been covered so far, we have established an approach for abstracting Pancake implementation to Viper specification. We have exercised the approach in a performant driver, and here's a preprint of the work on archive for more details. So now I'm going to briefly talk about some of my research ideas of compositionality of the Viper specification together to reason about concurrency. So as we can see from the demo, the example, that Viper model is basically sequential in the standard pre-post condition style. The problem is that it's not sufficient to express concurrency, say shared memory interaction between these PDs in SDDF. So just to step back a bit to see what we have at the moment. We have PD components implemented in Pancake. We have their abstracted specs, and we have a way of verifying that the implementation meets the spec. But the question is, how can we have a higher level view of the entire system using those individual pre-post condition specs? So my current approach is to use rely guarantee of composing a trace model. So just a brief introduction of rely guarantee to bring the context. Basically, we can treat the state transitions as the transition made by the environment, so other threads, and the transitions made by me, which is just the current program C. We have the standard pre-post condition in the rely guarantee quintuple, and we have rely condition, meaning that other threads can only make state changes satisfying that rely condition. So here, S0 and S1 has to satisfy the rely inv predicate, and similarly, the guarantee condition, meaning that my program can only make transition from S1 to S2 satisfying the guarantee predicate. So one way of connecting rely guarantee to our Pancake Viper front end is that we can have an interference Viper method to capture the rely condition of our current PD. So here, this interference, this post condition describe what can happen to the transition between old shared memory and the new shared memory made by changes made by the environment. And we can add, similarly, the guarantee condition to our shared operations, say, like share store or FFI calls to describe our guarantee conditions. And what we can do is we can add interference before and after every shared operation. So that's before, and then we have our guarantee, and we have interference after, so that we can describe a state transition model. So in this simple function, we can have a state sequence from S0 to 3 that satisfy our precondition, postcondition, and the rely guarantee quintuple. So once we describe these specs for our component, the proof obligation will become that the rely condition of one thread has to be obtainable by the guarantee conjunction of other threads. So for example, for the first thread, the driver thread, the R1 rely condition has to be implied by the conjunction of guarantees of our 2 to 5 PDs, and same as other PDs as well. So this part will be using the interactive theorem prover like Isabel, so that we can make use of some of the existing trace libraries, for example, like the L4V trace monad library off the shelf. So the overall process will be iterative, involving coming up with rely guarantee specs, the proof obligations of with other threads, and verify that the implementation, we have to fit it to the Viper toolchain to show that our implementation meets the spec. Right, and then with that model, we then can verify properties using the trace model. For example, like for network services, we can have receive, send client interface. We can verify the correctness properties of those calls, and possibly safety and liveness properties in terms of trace model invariance and lemmas. So just to summarize, with Pancake and its Viper support and further trace formalization, we hopefully can have a solution of systematic, repeatable approach for verifying not only device driver, but other lines OS system and, in general, SEO4-based OS services as well. The approach should require low effort with our Pancake verified compiler and automated mechanisms. It should have support for compositionality and deals with concurrency. And it applies to real-world actual performance system thanks to the development of SEO4 and its ecosystem. So that's all for my talk. I'd like to thank the support of SEO4 software system scholarship for my degree, and thank you so much for listening.
We are on. We have some time for questions, so please. Go ahead. Gavin.
The talking stick. Thank you. Great talk, thanks. I have a simple question. In the, you said it takes about 1 to 2 hours to run. Does that include the Pancake run or just the Viper?
Just the Viper, but the Viper is generated from Pancake.
Yeah, but it's not the binary verification part of it.
Just the Viper one.
Good. What is it doing in all that time? Like, is it mostly the transpiling or is it mostly the SMT solving?
I think it's mostly the SMT solver. So, like in the driver code, there are like bit operations like bit masking, shifting. I think that's one of the tricky thing for SMT solvers to figure out. Also, SDDF uses a shared queue with modular operation that can also be one of the tricky things for SMT solvers to figure out.
Cool, thanks.
But there are no analysis performance into that whatsoever.
Thank you for the talk. I'll directly join into that question. So after the 2 to 4 hours, what do I get, and how likely am I to be able to grok that input to make a change to my program so that after the next 2 to 4 hours it's correct?
So if it verifies, then it will say it verifies. If not, so Viper has pretty good support for error message that which condition doesn't satisfy.
So yes, we do have time for.
So we talked about this a little bit before, but I was wondering if you could just say a little bit about how you build the device, how you specify the device models in Viper. So do you give a sort of axiomatic semantics of MMIO on the device, or maybe you could just say a little bit about that?
I think for the current device model, it doesn't have the operations of the device, but more like the input, output, the possible range of input, output that we can fit into the device and what we can get from the device, if that makes sense.
Okay, so I think we do have time for another question if there is one. Otherwise, we'll thank the speaker. And thank you very much.